In today's lesson, we're going to be taking a look at continuous random variables for the first time. So over the past few lessons, we've been looking at how we deal with discrete random variables, and we talked about how when we want to look at quantities which are treated as continuous, we're going to have to use slightly different results for that. And so in today's lesson, we're going to start introducing those results, and we'll be looking at some of the extensions to what we've been seeing for the continuous setting over the next few lessons. So the primary objective of today's lesson is to understand what we would call the probability density function. Now, the probability density function is going to be the analog to the probability mass function when we're in the continuous setting. We'll also take a look at the uniform distribution, which is a continuous distribution, and we'll look at some of its properties. So we'll introduce sort of our first continuous distribution here. Now, by way of motivating example, we can think about running a timer, say, and in this case, it's a timer that's measuring to 3 decimal points, right? And we can ask ourselves how we would want to treat this variable. Of course, we could treat this as a discrete variable, right? We could group each of those 3 decimal points into different bins, right? And as a result, to get 1 second of coverage, you'd need 1,000 bins. And there might be times where that would make sense, right? If we're not going to be thinking about measuring times that would differ by multiple seconds, then you could get away with treating times as being discrete. But in the event here where, say, you could have times that range from, 0 to 25 seconds, say, in order to represent that in the discrete setting without rounding down to, say, the full second, you're going to have so many different bins that at some point it becomes infeasible to think about this as discrete. There's just too many possible outcomes. And so at some point it starts making sense to think about this as continuous. And in our day-to-day life, we do sort of think of time as a continuous quantity anyways, right? And so we'll do the same thing within our probability questions. And other quantities like height, like weight, are going to become better to think about in the continuous setting as well. So with discrete random variables, we thought about assigning probability mass to each of the different values that it could take on, right? So for any possible value of our discrete variable, we said this is what the probability that our random variable takes on that value. But we can start to think about why this is going to be an issue in the continuous case, right? If there's some interval that our random variable can take any value on, of course, there are infinitely many possible values that it could take on in this interval. But not only are there infinitely many, there are uncountably infinitely many. And so if we start to assign positive probability to each of these possible outcomes, we're going to quickly realize that there's no way we can do this and still keep a finite amount of probability being assigned. So what essentially we're saying is that we can't draw a probability map, right? If you think about a random variable defined on the interval 0 to 1, there's no way that we can say for 0, we get some probability, for 0.001, we get some probability, and so on for all the values, because you can't enumerate all of those values. And so if you were to have the probability that x takes on any value being greater than 0 for all of these, then what's going to happen to our full probability over our sample space? Remember that we know that we're going to want to add up all of these probabilities, right? And so if you were to assign probability to all of the possible values that you could take on, you're not going to be able to assign a sample space probability of 1. Right? And so we have to think about trying to approach probabilities in this case differently. There's just too many values in an interval in order to assign probabilities to them. But if you remember, we also defined what the cumulative distribution function was, and that was the probability that x was less than or equal to some value. And in a continuous case, this isn't really a hard thing to think about, right? We could take any value along our interval, again, say 0 to 1, and just say, for some probability, we're going to take values less than that, right? And because of that, we can start from the CDF as the way that we can define distributions for continuous random variables. So within the discrete case, we saw that the CDF was given by the summation of the PMF. And if we sort of approach a continuous setting, summations become integrals, right? If you think back to your calculus class, the way that you start to define an integral is to think about summing up the area under a curve, right? And then you make the boxes that you're summing over smaller and smaller and smaller. And so what we're doing in the continuous setting with random variables is we're thinking about taking a discrete random variable and making those intervals smaller and smaller and smaller until we're dealing with the whole continuous line. Right? And so if we think about summations becoming integrals, well, then we can sort of naturally generalize what the CDF has to be. So if we take our CDF to be capital F of x, then we make our summations into integrals. We can say that the CDF is going to be the integral of some function, which we'll call lowercase f, and it's going to be the integral from negative infinity up to the value x, right? And if you think about just the definition for a CDF in the discrete time case, all we've done here is we've replaced our probability mass function with this function f, and we're integrating instead of summing. Now, the fundamental theorem of calculus tells us that if we wanted to then differentiate our CDF, we're going to get back that function f of x over here, right? The lowercase f of x. And in some sense then, what this means is that this lowercase f of x is going to be analogous to the probability mass function, right? Because the PMF, we summed up to get to our CDF. And in this case, this function f of x here, we can integrate to get to our CDF. And so there's sort of this analog between f of x and the probability mass function we saw in the discrete case. And so what we're going to do is we're going to call f of x the probability density function, the PDF, right? And so we'll think about the PDF as basically being the PMF in the continuous time case. But there's going to be a few important differences to think about. And the reason that we're going to think about it as being analogous is because of this sort of relationship to the CDF, right? If you integrate a PDF, you get the CDF for a continuous random variable. If you sum the PMF, you get the CDF for a discrete random variable. Now, the PDF is going to characterize our continuous distribution. It could be plotted in a similar way to the PMF. The only difference is it's going to be a continuous curve. And the PDF is going to be thought about as representing some sort of relative likelihood of outcomes, but it's not going to represent probabilities directly. Remember, we said that the probability that x equals x for a continuous random variable, that it takes on any specific value, has to be 0. Because if it's bigger than 0, and it's bigger than 0 for any number of specific values, then we're going to end up in a situation where we cannot contain the probability over this whole sample space. Right? So it can't represent probabilities directly. But the idea is that if the PDF is high in a region, then the probabilities of observing something around that value are also going to be high. And if the PDF is low in a region, the probabilities around that value are also going to be low. And you can think about this related to the CDF, right? The CDF integrates the PDF, right? And so if you've integrated a lot of area, then you're going to have a high probability on the CDF. Now, if we wanted to find the probability of any event, we could think about the events being defined as x falling in some interval between a and b. And we can get this just by integrating the PDF, right? So if you want to know what's the probability that x falls between 0 and 1, you integrate from 0 to 1 of the PDF. We can represent this with respect to the CDFs as well in the exact same way that we did for the discrete time case. Now, we also require the PDF is going to be greater than or equal to 0 for all x, and it has to integrate to be 1 over the whole real line. Right? These are sort of the requirements from the similar requirements that we saw in the PMF. Now, as an example distribution, we can think about defining what we would call the uniform distribution. And it's maybe the easiest one to think about. The uniform distribution is going to generalize this concept of something being equally likely. Okay? So if we take some interval, just a to b, then the distribution known as the continuous uniform distribution is going to have a PDF, which is defined as 1 over b minus a if you're on that interval, and it's going to be 0 everywhere else. Now, I'll re-emphasize this point that the probability that at x equals some value is going to be 0 for any of these values, even if it's in the range, right? We're not going to have any probability that takes on any specific value. However, we can integrate this function to find the probability that it's in some range. Now, if we take some interval c to d, which is a subset of the original interval that we care about, then we can integrate this function from c to d, And if you do this integral, you'll find that the probability is going to be c minus d over b minus a. And if you think about this, this is going to, and there's a slight mistake in the slide here. This should actually be d minus c, right? The probability is not going to be a negative value, so we should get the probability is d minus c over b minus a, right? And if you think about this, this sort of makes sense, right? So if we take a is equal to, say, 0, b is equal to 1, right? So that the whole range is 1. And then we take, say, c is equal to 1/4 and d is equal to 3/4, right? Well, the interval 1/4 to 3/4 takes up 1/2 of the total interval 0 to 1, right? And so then if you were to get d minus c over b minus a, we're going to get 1/2 over 1, which is just 1/2. Right? So the probability should make some sense there. So that's the brief overview of how we define continuous random variables. We define them not to have a probability mass function, but a probability density function. We integrate the PDF to determine the probability of an event. Singletons, or single elements, are always going to have probability 0 in continuous random variables. And again, just to reemphasize why this is the case, if you were to take all of those values between 0 and 1 and give them some positive probability, well, then your probability is going to end up being infinite, and we can't have that. The uniform distribution we saw as a continuous distribution, which has equal density on the whole interval. And we saw how you can integrate over that to get particular probabilities. So we're going to continue working with density functions. We'll continue working with CDFs to start defining some of the related properties here. But the important thing to take away from this lesson is that a PDF is going to characterize the distribution, and it's going to be analogous, but not exactly the same thing as the PMF from the discrete case.